93 billion light years across, and you're at the center. How can that be? Observable universe means everything whose light has had time to reach you since the Big Bang. Not what's bright, not what's easy, just what can possibly arrive, given the age of the cosmos and the speed of light. Draw a bubble around you, defined by that rule. Its radius, in the mapping system cosmologists prefer, is about 46.5 billion light-years today. Double that for diameter, and you get roughly 93 billion light-years. You sit at the center by definition, because it's your past light cone. This bubble isn't a smooth wall. It's a 3D stack of earlier and earlier moments. Nearby galaxies show you a relatively recent frame of the story. Farther out, you're looking deeper into the past. Pushed to the limit, and the outermost surface you can see is not made of stars at all. It's a uniform microwave glow at 2.725 Kelvin, the cosmic microwave background. That's the fossil light, from when the universe cooled enough for electrons and protons to combine, about 380,000 years after the Big Bang. Before that, space was a hot, opaque plasma. Photons bounced around and couldn't travel far. When atoms formed, the fog thinned, and light started flying freely. Some of that light has been crossing expanding space ever since, arriving today as microwaves. That's the true far wall of visibility. Now, bring James Webb into the frame. Webb does not observe microwaves. Webb is built for infrared. Why infrared? Because the light from the first generations of stars and galaxies started out bluer, but space has stretched while that light travelled. Expansion drags wavelengths longer. Ultraviolet and visible light from the earliest galaxies gets redshifted into the infrared by the time it reaches us. That's exactly where Webb's instruments are most sensitive. So Webb doesn't take the baby picture, that's the CMB, but it does map the first galaxies that formed just after the cosmic fog cleared. Think of it as charting the near side of that ancient shell, not the wall itself, but the frontier just inside it where the first structures switch on. Webb's advantage is simple: area, stability, temperature, and the right tools. A segmented mirror collects faint photons. The observatory sits far from Earth's thermal noise. The sunshield keeps it cold so the instruments don't glow and drown out the sky. NIRCam captures insanely deep images in the near-infrared, pushing down to tiny red faint smudges that would have been invisible before. Then spectroscopy turns those smudges into measurements you can trust. Split the light, see the fingerprints of hydrogen, oxygen, and other lines, and extract a precise redshift. That redshift is your distance proxy. It's how you convert a color shift into a position inside your 93 billion light-year volume. The moment you measure a redshift is, you do more than pin a dot on a map. You also tag a time. That galaxy's light left when the universe was only a few 100 million years old. You can then ask, how big was it? How fast was it forming stars? How much dust had already built up? How enriched were its gases? Those answers are not trivia. They tell you whether we're seeing a quiet, slow build-up or a violent, rapid assembly of structure. Webb's early results are blunt. Things got big fast. We're finding surprisingly luminous, surprisingly compact, surprisingly evolved system earlier than expected. That doesn't break cosmology, but it does force sharper models of how gas cooled, collapsed, and lit up. Let's be clear about the meaning of observable. It is a time limit, not a brightness limit. There are galaxies well inside your bubble that are simply too faint for any telescope today. There are bursts of light that were absorbed or scattered before they could reach you. Observable says nothing about whether you can actually detect a given source. It only says the light could, in principle, be here by now. This is why better instruments make your bubble feel fuller without changing the bubble's formal size. Webb expands the catalogue of what's actually seen, filling in the census out toward the horizon. That outer microwave surface matters for another reason. Its tiny temperature ripples, tens of microkelvin, are a blueprint of the initial conditions. They seed the large-scale web of matter that later grows into galaxies and clusters. When you align Webb's high redshift galaxies with those expectations, you're testing the entire story, from early ripples to first stars to mature galaxies, all inside one self-consistent frame. If the counts, sizes, and star formation rates line up, confidence climbs. If they don't, you learn exactly where the modelling is thin. You might worry that you're at the centre. Sounds like a claim about importance. Drop that. The centre is only the point where the light arrives. Every observer anywhere is at the centre of their own observable sphere. This is a consequence of a finite light speed and a universe that looks statistically the same in all directions on very large scales. That symmetry, the cosmological principle, is what lets you even talk about a single radius like 46.5 billion light-years without tripping over direction-by-direction exceptions. There's a second subtlety. The sphere you can see today is not the sphere you'll be able to see in the far future. As time passes, you'll receive new photons from slightly farther comoving distances, so the observable boundary inches outward. But accelerated expansion also creates an event horizon. Regions so far that light emitted there today will never reach you. Ever. That's a different limit. It doesn't change the 93 billion light-year number for the present observable diameter, but it does cap what will be knowable in the long run. Webb can't change horizons, it can only harvest everything the current horizon allows. So here's the bottom line of this opening. You live at the centre of your own time-defined bubble. The far wall is the 2.725 Kelvin CMB. Webb doesn't see that wall, but it drills into the layer right in front of it by catching infrared from the first galaxies. The result is a sharper, denser map of the early universe, anchored to the same geometry that sets the 93 billion light-year scale. Now, the hard question you should ask next is simple and uncomfortable. The universe is about 13.8 billion years old. So how can anything be 46.5 billion light-years away? And what exactly does away mean in an expanding universe where distance itself changes while the light is in flight? How can you see something 46.5 billion light-years away when the universe is only 13.8 billion years old? Start by fixing the word distance. In cosmology, it isn't one number. You have lookback time, which is how long the light has been travelling, proper distance, which is the physical separation at a specific cosmic time, and comoving distance, which factors out the overall expansion so positions don't drift as the universe grows. The 46.5 billion light-year radius is a comoving distance, not a travel time, and that is why the number can be bigger than the age in years. Lookback time is the easy one. It's the age stamp on the photon that arrives at your detector. A galaxy with a lookback time of 13.2 billion years sent that light when the universe was young. Proper distance depends on when you ask, how far? Because the gap stretches while the photon is en route. Comoving distance gives you a stable coordinate, so a point keeps the same label even as space expands. When people say the observable universe is 93 billion light-years across, they mean the current comoving diameter, double the approximately 46.5 billion light-year radius. Here's the clean picture. A photon leaves a very distant region. The universe expands while it flies, and by the time it reaches you, that region is now much farther away than it was at launch. The light's travel time might be 13.4 billion years, but the comoving distance to where it came from today can be tens of billions of light-years. Example, ballpark numbers, not a trap. A galaxy at redshift 10 emitted light when the universe's scale was about 1/11th of today, so its proper distance back then was far smaller. Yet its comoving distance now is roughly 30 plus billion light-years. Redshift is the handle that turns colour into distance. It tells you by what factor the wavelengths were stretched. Bigger redshift, more stretch, older epoch, larger comoving distance. To convert redshift into an actual number, you need a cosmological model, a set of parameters that act like a ruler. The community baseline is lambda CDM, a flat universe dominated by cold dark matter and dark energy. With Planck-calibrated values around H0, approximately 67.4 kilometers per second per megaparsec matter density. Omega M approximately 0.315, and an age of about 13.8 billion years, you can integrate the expansion history and get consistent lookback times, proper distances, and comoving distances for any redshift you measure. This is why the 46.5 is honest. It comes from the expansion history implied by that baseline model, run all the way back to the first light we can ever see. That particular radius has a name, the particle horizon today, meaning the farthest comoving place whose light has had time to reach you since the universe became transparent. It's not the path length the photon travelled through stretching space, it's the current distance to the region that emitted the earliest possible signal you can receive now. There's a second, different horizon you need to keep straight, and it cuts the other way. Because the expansion is accelerating, light emitted today from beyond roughly 16 billion light-years in proper distance will never reach you, not in any future. That's the event horizon. It does not change how far you can see right now, but it sets a hard cap on what brand new signals can ever arrive from this day forward. So the 93 billion light-year observable bubble is not the same as the ultimately knowable universe across all time. Put the pieces together, and the paradox dissolves. 13.8 billion years is a clock, 46.5 billion light-years is a comoving length derived from that clock, plus the measured expansion history. Travel time and present-day separation are different questions, therefore different answers. Once you choose the right definition for the job, the numbers line up and stay consistent across the CMB, galaxy surveys, and high redshift targets. This in turn tells you what the telescope has to deliver. You need precise redshifts to anchor distance, you need sensitivity to catch faint stretched light from early times, and you need efficient spectroscopy so you can turn deep images into a three-dimensional map. That's the only way to put reliable pins into a 93 billion light-year atlas without fooling yourself with rough Collier guesses or photometric maybes. One more practical note before we move on. People often mix proper distance then with proper distance now, or treat lookback time like a ruler. Don't. When you read a result, ask which distance is being quoted. If it's a travel time, it'll be near the age of the universe for the farthest things. If it's comoving, it can be several times larger. If it's proper distance at emission, it will be much smaller. Same sky, different yardsticks, different valid answers. So the next step is obvious. Which tool can actually collect enough photons, split them cleanly, and measure hundreds of redshifts at once so you can scale the early universe correctly? You need a cold infrared optimized observatory with the right cameras and spectrographs to turn faint smudges into hard distances. That is where James Webb's toolkit changes the map and changes the pace. You want hard distances, ages, and growth rates from the earliest galaxies, fast, so what hardware makes that possible, and why does it change the map you carry in your head? Start with NIRCam. This is Webb's near-infrared camera, the deep field workhorse. It stares long, stacks exposures, and pulls out tiny red, faint smudges that older telescopes simply missed. Those smudges are stretched galaxies. Their light shifted into the infrared by expansion. NIRCam uses multiple filters, short and long wavelength channels, and very stable optics, so you can separate real high redshift candidates from lookalikes. You get sharp images, precise colours, and positions clean enough to feed a spectrograph without wasting time. Bottom line, NIRCam finds the targets at the edge of what's detectable, and it does it with the depth and cleanliness needed for follow-up. Now you need redshifts you can defend. That's NIRSpec. This spectrograph covers roughly 6/10 to a little over 5 microns, and it gives you choices in resolving power, from about 100 for quick, faint work, up through about 2700 for line separation and kinematics. You pick the mode based on the job. At low resolution, you catch ultra-faint continua and big spectral breaks. At medium and high resolution, you isolate emission lines like hydrogen's Lyman-α when it gets through, the Balmer lines including H-alpha where accessible, and strong oxygen lines that carry the load at very high redshift. With those lines separated cleanly, you lock the redshift, not as a guess, but as a measurement with error bars you can quote. Here's the feature that turns a pretty picture into a 3D survey: the microshutter array. Think of about 248,000 tiny doors, each one addressable. You program a custom masking software, open a pattern that matches your targets, and close the shutters on sky you don't want. One pointing, hundreds of spectra at once, minimal contamination from neighbours, and efficient use of every minute in the field. That is how a single deep image becomes a dense set of distances, ages, and star formation rates, not over years, but in campaign-length blocks. Modes matter because you do not always want many at once. Sometimes you want everything about one galaxy. Integral field spectroscopy gives you a data cube, 2 dimensions of position and one of wavelength, so you can map how gas moves across the galaxy, measure rotation, dispersion, outflows, and shocks. You get line ratios across the face of the source, so you can probe metallicity gradients, dust, and ionization. For large samples, multi-object mode wins. For diagnosis, the integral field unit wins. Webb gives you both. Add in fixed slits for clean, bright sources, and slitless options from the other instruments when you want wide surveys, and you have a full kit. What does this buy you in practice? First, distances you can place on a comoving map inside the 93 billion light-year bubble. Second, stellar ages and masses from the overall spectral shape and breaks. Third, star formation rates from recombination lines like H-alpha when in range, or from oxygen and hydrogen proxies when H-alpha slides beyond NIRSpec's band. Fourth, gas metallicities from line ratios, which tell you how quickly stars have been forging heavier elements. Fifth, dust content from line to continuum comparisons and ultraviolet slopes, which lets you correct for hidden star formation. The observatory's layout solves the background problem too. Webb sits cold in deep space behind a multi-layer sunshield. That keeps its own thermal glow out of the data, so the noise floor drops, and the faintest galaxies stay visible. The image quality is stable, so you can dither, reject bad pixels, subtract residual backgrounds, and co-add to extreme depth without the stacks falling apart. That stability is why you can trust differences at the few % level across filters, which is exactly where high redshift selection lives. Operationally, the pipeline is tight and repeatable. NIRCam selects candidates with color cuts that track the Lyman break and other features. The team designs a microshutter configuration, opens those specific doors, and runs NIRSpec in the right resolution for the science goal. The spectra come back with identifiable lines and breaks. Redshifts drop out. With redshifts in hand, you fit stellar populations, derive ages and masses, estimate star formation rates, and flag active nuclei when line widths and ratios demand it. One field at a time, you turn 2-dimensional pictures into 3-dimensional maps with timestamps. Coverage across wavelengths is the quiet superpower here. From about 0.6 to 5+ microns, NIRSpec catches different rest frame features as redshift grows. Oxygen 3 lines slide into the band at very high redshift. Hydrogen Balmer lines run through at mid-redshift, and the Lyman break moves across the filter set, giving you multiple independent handles. Where H-alpha redshifts beyond NIRSpec, mid-infrared modes pick up some of the load, so you still have routes to star formation and dust. The result is continuity, not gaps, which keeps the early universe timeline connected rather than stitched from mismatched surveys. Scale is the other lever. Because the microshutter array multiplexes efficiently, you do not just confirm a handful of cases. You build samples large enough to see distributions, not just outliers. You can measure how common, bright, compact early galaxies really are, how their star formation rates spread, how their metallicities cluster, and how their numbers change with redshift. That is the difference between a headline object and a population result. And population results are what change theory. Pull the threads together. NIRCam finds the faint stretch targets. NIRSpec nails their redshifts across roughly 0.6 to 5.3 microns at resolutions around 100, 1000 and 2700. The microshutter array turns each deep image into hundreds of spectra per pointing. Integral field and multi-object modes let you weigh galaxies, age their stars and measure their gas. Translation, you get distances, ages and star formation rates at scale, with the confidence needed to place those dots inside the 93 billion light-year bubble, not as guesses, but as coordinates with uncertainties. If the toolkit is this strong, the next question is obvious. And the stakes jump. How far back did Webb actually confirm galaxies? How bright were they? And do those record setters force us to speed up our story of how structure formed? How early is too early for a real galaxy? With stars, structure, and heavy elements, and not just a hopeful smudge. Webb's answer is blunt, earlier than you expected. Teams working with the JADES program confirmed galaxies near redshift 14, including JADES GSZ 14-0, which means you're seeing it about 290 million years after the Big Bang. That is not a placeholder date from color cuts. That's a spectroscopic age stamp. It shaves precious time off the window between the first cooling gas and the first mature systems, and it forces you to accept that structure formation ramped up fast. Numbers matter, so keep them straight. JADES GSZ 14-0 is roughly 1,700 light-years across, compact but not tiny, comfortably a real galaxy. Its star formation rate is around 20 solar masses per year, which is aggressive for such an early epoch. For context, the Milky Way now sits at a few solar masses per year, and it had billions of years to settle into that pace. So at Z approximately 14, this thing is punching far above its weight, turning gas into stars at a rate that challenges simple slow-growth pictures. The key upgrade here is method. This is not we measured red colours and guessed a redshift. Webb's NIRSpec delivered spectra that show the sharp, telltale Lyman break. Bright redwood, basically nothing bluewood, exactly where an object at Z approximately 14 should put it. Where lines are accessible, they show up with the separations you expect at the quoted redshift. Where Lyman-α is suppressed by neutral hydrogen, the continuum break still nails the distance. That is what spectroscopic confirmation means, a locked solution, not a photometric maybe. Follow-up in complementary bands, when available, backs up the fit rather than rescuing it. Why does one galaxy or a handful matter this much? Because they anchor the timeline at the high redshift end with hard data. If you can populate Z approximately 10 to 14, with secure distances and physical properties, you stop arguing about whether the early universe was full of imposters and start measuring how quickly halos assembled, how efficiently gas cooled, and how early heavy elements appeared. A size near 1,700 light-years and a star formation rate near 20 solar masses per year imply dense gas, rapid fueling and feedback strong enough to shape the next generation of stars, all inside a system that had less than 300 million years to form. This shifts your internal map, the outer microwave wall, the CMB at 380,000 years was always there, but the first bright confirmed galaxies are now pressed closer to that wall than you were willing to bet a few years ago. The gap between baby universe and first mature structures is thinner. That doesn't increase the formal size of your 93 billion light-year bubble, but it makes that bubble feel more occupied earlier, with more mass, more light and more chemistry on the board sooner. Look at the physical readouts you get once the redshift is fixed. Stellar mass estimates rise quickly when you allow for sustained 20 solar mass per year building. Specific star formation rates point to very young stellar populations, which matches the timeline. Line ratios, when available, point to non-primordial gas, meaning at least one prior round of starbirth and death already seeded heavier elements. That pushes models toward efficient early cooling channels and rapid enrichment, not a long, quiet dark age. And no, this result does not break the underlying cosmology by itself. Lambda-CDM can accommodate early bright systems if you dial the star formation efficiency and feedback knobs within observational bounds. What it does break is complacency. It reduces the wiggle room for theories that spread early growth too thin. It favours scenarios where small halos form stars earlier, merge often, and briefly achieve high surface brightness before feedback throttles them. The detection mode is also a message about survey strategy. Deep NIRCam imaging finds the candidates. The microshutter array in NIRSpec opens on hundreds of them per pointing, and the spectra convert a pretty field into a 3D catalogue. You get robust counts, not just showpieces. With statistics, you can test luminosity functions, check how many bright objects you should expect at ZID, approximately 12 to 14, and see whether JADE's GSZ 14.0 is a rare outlier, or the bright tip of a larger population. Early indications say the bright end is busier than older models predicted. All of this tightens the connection to the microwave background. The CMB maps the initial density ripples. Galaxies like JADE's GSZ 14-0 are those ripples grown up. When you confirm them spectroscopically this early, you validate the path from microkelvin fluctuations to real luminous systems in under 300 million years. That locks your geometry and your growth history together. And it shrinks the timeline for the first rounds of star formation and metal production. So ask the next hard question. If galaxies were already this active at Z approximately 14, their ultraviolet light had to be blasting into the intergalactic medium, breaking apart neutral hydrogen and carving ionized bubbles. Did the fog lift earlier than we thought? And can we prove it by catching the right spectral lines from even deeper targets? How do you know when the universe turned the lights back on, and did it happen earlier than you were told a few years ago? Start with the clean constraint we already have. Planck measured how many free electrons the CMB photons scattered off on their way to us. A quantity called the Thomson optical depth, tau, about 0.054 to 0.059. That single number compresses the whole history of reionization into one integrated effect, and when you run it through the standard model, it points to a midpoint of reionization around redshift 8. Translation: by Z approximately 8, the intergalactic hydrogen was roughly half ionized, and the rest was on its way. Now look at what Webb is actually seeing. Lyman-α, the bright hydrogen line that sits in the ultraviolet at the source, is extremely easy to scatter if the gas between you and the galaxy is still neutral. A mostly neutral intergalactic medium should kill the alpha's transmission from very early galaxies. Yet Webb is now detecting Lyman-α from some galaxies near redshift 13. That is a hard clue. You don't get a clean Lyman-α line through a neutral medium unless the galaxy sits inside an ionized bubble big enough to let the photons redshift out of resonance before they hit neutral gas. Finding Lyman-α that early means those bubbles existed surprisingly soon, which means there were already enough ionizing photons leaking into space to carve holes in the fog. Here's the logic you can audit. Pick a redshift slice, collect a sample of galaxies selected by NIRCam colours that indicate high redshift. Then point NIRSpec and look for Lyman-α at the expected wavelength. Count detections versus non-detections. The fraction that show Lyman-α and the line shapes you see track the neutral fraction of the intergalactic medium at that time. When the universe is mostly neutral, Lyman-α is rare, and the lines look damped and skewed by absorption. As the neutral fraction falls, Lyman-α shows up more often, lines get stronger, and you can even start measuring velocity shifts that tell you about outflows and local gas kinematics. Programs like SEERS and JADES make this statistical, not anecdotal. EARS spreads across multiple pointings to limit cosmic variance. JWST goes deeper in smaller fields to reach fainter, earlier systems. Both use NIRSpec's multiplexing to grab hundreds of spectra in a single setup, so you don't get fooled by a small number luck. With each pointing, the catalogue of confirmed redshifts grows, and the LYA detection rate as a function of redshift sharpens. That curve, when compared with radiative transfer models, maps the neutral fraction over time. You move from maybe early bubbles exist to Here is the redshift-dependent ionization history with uncertainties. Details matter here, and they're straightforward. If Lyman-α is shifted a few hundred kilometers per second to the red by outflows inside the galaxy, it has a better chance to escape both the galaxy and the partially neutral intergalactic medium. That helps, but it isn't magic. You still need large ionized regions around the source if the global neutral fraction is high. When Webb sees Lyman-α at Z approximately 13 with decent signal, the simplest reading is that local ionized pockets were already a thing. Combine that with non-detections in other sightlines at the same redshift, and you get a patchy picture, exactly what you expect during reionization. Islands of transparency in a mostly neutral sea. Planck's tau and Webb's Li-alpha are not in conflict. Tau is an integral of the whole path from last scattering to now, one number summarizing billions of years. Lyman-α is a local tracer at a specific redshift. If the midpoint is near Z, approximately 8, you can still have significant, earlier ionized bubbles at Z approximately 12 to 13, as long as the global average remains high. Webb's detections tighten the timing and the photon budget. They tell you galaxies must have been producing and leaking ionizing photons efficiently, earlier than many conservative models assumed. That pushes you to measure the escape fraction, the star formation rates, and the initial mass function in those early systems with more care. This is where the spectra turn pretty pictures into a map you can use. A photometric dropout alone can't tell you whether the line is present, how strong it is, or how the damping wing eats into it. NIRSpec shows the continuum break, the line profile, and the neighbouring diagnostic lines when they fall in band. With that, you can separate true high redshift sources from dusty lower redshift imposters, and you can quantify line equivalent widths without wishful thinking. Stack many, and you reduce noise, keep them separate, and you preserve the field-to-field variance you need to understand patchiness. Do both, and you get a robust reionization history, not a story built on 2 or 3 spectacular objects. Now tie it back to scale. Your 93 billion light-year observable bubble is not just a distance, it's a timeline. Reionization is the switch that made most of that timeline visible in starlight. Pinning down when and how fast the fog lifted tells you how quickly structure filled that volume. If Lyman-α appears at Z approximately 13 in multiple fields, the inside edge of your mental map shifts closer to the CMB in a meaningful way. It says galaxies, not just dark halos, were active early, pumping out ultraviolet photons, heating and ionizing their neighborhoods, and changing the transparency of space on short timescales. There are checks and caveats, and you should keep them in view. Foreground contamination is handled by spectra, not colors. Gravitational lensing can boost fluxes and bias counts if you don't model it, so fields with good lens models are valuable. Outflows alter line profiles so you compare Lyman-α with non-resonant lines when possible to avoid overreading velocity shifts. And cosmic variance is real, so Sears style area complements Jade's style depth. None of these erase the main signal, they just keep the error bars honest, so the picture is tightening. Planck sets the overall timing tau around 0.054 to 0.059 and a midpoint near Z, approximately 8. Webb adds direct line-based evidence that ionized bubbles existed by Z approximately 13 in at least some regions. Counting where Lyman-α gets through, and how the profiles look, lets you trace the neutral fraction as a function of redshift, turning deep images into a 3D reionization map with real confidence. That is what it means to upgrade a pretty field into cosmic cartography. If early galaxies were already carving holes in the fog, the obvious next move is to reach even fainter sources and even higher redshifts, but there's a limit to sensitivity in any fixed exposure. So how do you push beyond the normal depth of your telescope and sample more of the early universe per shot? How do you go deeper than your mirror should allow and pull galaxies out of the noise that should be invisible? You use gravity as a lens. Webb's first deep field pointed at the cluster SMACS 0723, massive knot of galaxies and dark matter. Its gravity bends space-time, deflects light, and magnifies background galaxies that sit far behind it. The result is stretch and boost, arcs, and multiple images, and crucially, extra flux. With magnification factors of several to tens, sometimes more, galaxies that would be below Webb's detection limit pop up in view, and your reach into the early universe jumps. This isn't a vague effect, it's geometry you can measure. NIRCam delivers razor-sharp images of arcs and counter-arcs. You see mirrored structures, repeated clumps, and color patterns that give away which images belong to the same source. Then NIRSpec adds the lock. You take spectra of the cluster members to nail the lens plane, and spectra of the arcs to pin background redshifts. With redshifts on both sides, you solve for the mass that makes the observed image positions and shapes, and you iterate until the lens model reproduces the data cleanly. Data in, model out, not guesswork. Why does this change the map? First, magnification pushes you to fainter intrinsic luminosities at high redshift. The steepness of the early galaxy luminosity function means that boosting faint sources over the detection threshold increases the number you can study per exposure. This is magnification bias working for you. Second, multiple images give you redundancy. Measure one, check the others, average out noise, catch systematics. Third, the lens model lets you delens each galaxy, recovering its true brightness and size in the source plane. You stop confusing bright because lensed with intrinsically extreme, and you get honest physical parameters. Lensing also pays off on the foreground side. The only way to produce those precise arcs and multiple images is with a specific mass distribution. By fitting the arcs, their separations, and their parity flips, you build a dark matter map of the cluster. The luminous member galaxies contribute, but most of the mass is dark. The final product is a high-resolution mass model, where the cluster's matter is densest, where the critical curves run, where the caustics fold. That is the scaffolding of large-scale structure inside your 93 billion light-year volume, observed directly through its gravitational effect. Here's how a typical SMACS 0723 style sequence runs. Step 1. Deep NIRCam imaging reveals dozens of candidate lensed systems, plus rich detail in cluster members. Step 2. You select sets of multiple images by morphology and colour, cross-match them, and prioritise for spectroscopy. Step 3. NIRSpec measures cluster member redshifts to fix the lens plane, and background redshifts to anchor the source plane. Step 4. You feed all constraints, image positions, shapes, parity and redshifts, into a lens modelling code, blending strong lensing constraints near the cluster core with weak lensing shear farther out. Step 5. You apply the model to each arc, delens it and infer the intrinsic size, luminosity and star formation rate of the highest galaxy. Every step is tied to data with uncertainties you can propagate. A few practical gains show up immediately. You access compact sources at Z greater than 10 with effective spatial resolutions better than Webb's native beam once lensed, letting you study clumps, gradients, and potential rotation on sub-kiloparsec scales. You detect emission lines that would otherwise sit below the noise, because magnification lifts them into NIRSpec's reach. You can even get velocity information when you resolve lines at higher spectral resolution, translating line widths into dynamical masses. Put together, you aren't just spotting early galaxies, you're measuring them. There are caveats, and you handle them up front. Magnification varies across the field, so you carry a magnification map with uncertainties. Source plane area shrinks when magnified, so you correct number counts for that loss. Cluster member light can contaminate arcs, so you model and subtract it carefully. Line of sight structures can perturb the lensing potential, so you include them when spectra reveal additional planes. None of this erases the benefit, it just keeps the error bars honest and the population statistics clean. SMACS 0723 proved the point on day 1. Webb's depth plus the cluster's magnification turned a single pointing into a catalogue of high redshift galaxies, some at extreme distances, many with spectra in hand. The speed of that return is the story. One exposure, many arcs, hundreds of spectra, and immediately new constraints on the faint end of the luminosity function, the prevalence of compact starbursts, and the timeline of early enrichment. That's more cosmic real estate sampled per hour, not by sleight of hand, but by letting gravity do free optical work. The dark matter map you derive from the same data is a second win. Strong lensing features fix the inner potential. Weak shear patterns extend the map outward. Compare the mass map to the light from cluster galaxies, and you test how baryons and dark matter cohabit dense environments. Add X-ray or Sunyasev-Zeldovich data when available, and you start to separate hot gas from collisionless dark matter. These comparisons sharpen models of structure growth inside your observable bubble, using one field to teach you about the physics that shapes all clusters. Net effect, a lensing deep field is a depth multiplier and a physics lab at once. You see fainter, you measure more precisely, and you learn about both the background universe and the lens itself. For early universe work, that means more secure redshifts, better intrinsic sizes and luminosities, and larger, more complete samples at ZIGD greater than 10. For structure formation, it means mass maps that anchor simulations and sharpen predictions for how galaxies live inside the cosmic web. This raises the next scale question. You've used gravity to boost your reach and to weigh the scaffolding. But to set the size of the whole map, and to pin down distances across billions of light years without relying on any one cluster, you need a built-in yardstick written into the distribution of galaxies themselves. What ruler in the sky lets you measure expansion and lock the geometry that defines your 93 billion light-year bubble? How do you measure distances you will never visit and check that your map isn't drifting with every new survey? You use a built-in yardstick that the universe left behind. That yardstick is the Brion acoustic oscillation scale, about 150 megaparsecs in comoving units. It comes from pressure waves that move through the hot plasma before recombination, stopped when atoms formed, and froze in as a faint preferred separation between overdensities. Translate that into today's sky, and you get a standard ruler you can see statistically in the clustering of galaxies and quasars. The first clean detection in galaxy positions came from SDSS. Stack millions of galaxies, calculate the 2-point correlation function, and a weak bump appears at the BAO scale. It's not a single object, it's a pattern across the whole distribution. Because the scale is set by early universe physics and calibrated by the CMB, it's stable. That stability is the point. Measure the ruler across redshifts, and you watch how distances along and across the line of sight change with time. The transverse BAO gives you angular diameter distance. The radial BAO gives you the expansion rate h of the universe at that redshift. Do both, and you pin geometry and growth without relying on any single galaxy's brightness or any one supernova's calibration. Now scale up to current surveys. DESI's massive redshift campaign, is DR2 in 2025, maps tens of millions of traces across a huge volume, covering roughly 11 billion years of lookback time. That span means you don't just get a snapshot, you get a timeline of BAO measurements from the recent universe back into the epoch when quasars and the Lyman-α forest take over as tracers. With that timeline, DESI extracts distances as a function of redshift and h of z directly from the anisotropic BAO signal, percent level in multiple bins. Those are anchor points spread through cosmic history that any expansion model must hit. BAO does not work in isolation. Combine BAO with the CMB and you tie late-time distances to early-time physics. The CMB sets the sound horizon at recombination and nails the shape of the initial fluctuation spectrum. BAO measures how that fixed scale projects onto the sky at later times. Together they lock global curvature to be very close to flat and set the overall distance-redshift relation that defines your map. That is the quiet way you justify quoting a present-day comoving radius of about 46.5 billion light-years for the observable universe. The number isn't a guess, it is geometry backed by two independent pillars. Where does Webb fit? Webb isn't a wide-area redshift factory like DESI, but it is precise where ground-based surveys struggle. The high redshift end where lines are pushed deep into the infrared and galaxies are faint. NIRSpec delivers secure redshifts for early galaxies, including regimes where optical spectrographs fall off. Those redshifts feed two roles. First, they validate photometric redshift techniques used over large areas, reducing biases that would smear the BAO signal at high Z. Second, they open the door to future infrared-enabled BAO measurements in the early universe by proving that dense, reliable redshift samples are achievable beyond Z, approximately 2 with space-based spectroscopy. Make the mechanics clear. BAO comes from statistics, not single targets. You measure clustering over huge volumes, correct for selection effects, and compare with mock catalogues to control systematics. You fit the anisotropic correlation function or the power spectrum, find the BAO peak positions along and across the line of sight, and translate them into DMZ and HZ. The uncertainties propagate cleanly. Cross-check with different tracers, luminous red galaxies, emission line galaxies, quasars, and the Lyman-α forest, and you stress test the answer. If each tracer lands on the same distance ladder within errors, confidence climbs. This approach does something powerful for your map. It decouples distance measurement from the local distance ladder. Supernovae and Cepheids build the ladder nearby and give reach to intermediate redshifts. BAO nails down the relative scale across most of cosmic time, anchored by the CMB. When both agree on the same geometry, you have a robust expansion history. When they do not, you learn exactly where the tension sits. Either way, you are not stuck with one method or one set of assumptions. There's also a practical payoff for everything Webb measures. Precise high-Z redshifts let you match early galaxy populations to the BAO-calibrated distance grid. That means the sizes, star formation rates, and luminosity functions you infer sit on a distance scale that is already cross-checked by BAO and CMB. Fewer sliding parts, fewer hidden degeneracies. When you say an object at Z approximately 10 has a certain intrinsic luminosity or size, that statement inherits stability from the same ruler that SDSS first saw, and DESI now refines. So you have a yardstick fixed by early physics, read out by giant surveys, and tied to the same geometry that sets your 93 billion light-year diameter. That should make one question unavoidable. If BAO plus CMB point to one expansion rate today, but the local distance ladder points to a faster one which tape measure sets the scale, and what does that do to every distance you quote? 2 tape measures, 1 universe. Which one do you trust? The early universe route, using the CMB in a well-tested model, lands on an expansion rate today of about 67.4 km per second per megaparsec. The local route, the distance ladder built from parallax to Cepheids to Type Ia supernovae, lands near 73. That 5 to 6% split sounds small, but it propagates into every distance and age you infer from redshift. It shifts timelines, it tweaks volumes, it changes how fast structure must have assembled. Here's the clean separation. The Planck result is an inference. Measure the microwave background in exquisite detail, fit lambda CDM, evolve that physics forward, and read off H0. It is global, model-anchored and unbelievably precise. The SH0ES result is direct. Measure geometric parallax to Milky Way Cepheids, calibrate their period luminosity relation, observe Cepheids in host galaxies of well-measured type Ia supernovae, and propagate that calibration to the Hubble flow. It is local, ladder-based, and carefully audited. Both are internally consistent. Together, they disagree beyond their quoted errors. That's the tension. What can Webb do here? Attack the weak points in the ladder. HST photometry of crowded Cepheid fields risks blending, where unresolved neighbours make Cepheids look brighter than they are. JWST's sharper infrared vision and lower background reduce that crowding, and the longer wavelengths cut dust extinction at the same time. Teams reimaged key supernova host galaxies, measured the same Cepheids with NIRC, AM and NIRSS and compared against HST, the verdict so far is blunt. Improved resolution and dust handling do not erase the offset. 0 points, crowding and calibration have been tightened, but the local H0 stays high within errors. Webb's checks go wider than Cepheids. Tip of the red giant branch distances benefit from infrared imaging that resolves the brightest red giants cleanly in metal-rich hosts, reducing population-dependent biases. Surface brightness fluctuations, mirrors, and geometric maser anchors can all be cross-calibrated with deeper, cleaner infrared photometry. Each step looks for the kind of hidden bias that could slide the ladder down towards 67 without breaking anything else. So far, no single correction is big enough. The stakes stay high. Why does this matter to your map? Because the conversion from redshift to distance depends on the whole expansion history, with H0 setting the overall scale. Change H0 by a few percent, and the comoving distances you assign at fixed redshift nudge by comparable amounts. Ages at a given redshift shift by hundreds of millions of years at the earliest times. Star formation rates derive from luminosity's shift when distances shift. Halo masses derived from dynamics and sizes move with them. The 93 billion light-year headline diameter, however, is buffered by the combined BAO plus CMB geometry alter H0 within today's bounds, and the particle horizon radius today moves only slightly. Your top-line eyes remain stable, even as the ruler's tick marks are being re-etched. There's another angle you should keep in view. Independent probes, BAO with supernovae, time delay lenses, strong lensing velocity dispersion combinations, gravitational wave standard sirens, and dispersion measures from fast radio bursts are converging on the same question from different systematics. BAO plus BBN tends to support low H0, lensing often sits in the middle to high, sirens are improving quickly. Webb strengthens several of these by supplying clean host imaging, secure redshifts, and better dust and crowding control. The more probes you can cross-lock, the more obvious it becomes whether this is new physics or unmodelled systematics. So what's the practical takeaway for you as you place dots inside the 93 Glee bubble? Treat the radius as secure, because it rides on geometry constrained by the CMB and BAO. Treat the path to that number as active work, because small changes in H0 ripple through your inferred luminosities, sizes, and formation times. Webb is not rewriting the headline size, it is stress testing the calibration that turns spectra into distances and ages, and so far, it is keeping the tension alive rather than quietly dissolving it. If scale is set, you still need structure, and that's the next lever on your intuition. On the largest scales, the universe smooths out, but inside that bubble, matter gathers into filaments, sheets, and vast empty regions. How big do these structures get? How do they connect? And what does Webb add to the picture of the cosmic web you live inside? If the universe is supposed to be smooth on large scales, why do you see walls of galaxies, skinny bridges, and giant empty holes? Because gravity didn't paint the sky evenly, it amplified tiny early ripples. Dark matter pulled first, gas followed the pull, and galaxies lit up where the matter piled in. That network is the cosmic web, a pattern of filaments, sheets, and voids that runs through your whole observable bubble. Galaxies don't live in isolation, they sit on these threads, and the busiest intersections, nodes, grow into clusters. Scale this in plain numbers. Filaments can run for hundreds of millions of light years, voids can be tens of millions of light years across, and the biggest contiguous features stretch even farther. The Sloan Great Wall, mapped by SDSS, spans about 1.37 billion light-years end to end. That's huge for a single structure, but put it next to a 93 billion light-year diameter universe and it's small. A bump on a much bigger canvas. This is the key point. You can have monster structures and still keep the big picture simple. How do you keep the big picture simple? You average over enough volume. above scales of roughly 100 megaparsecs, think 300 million light-years, the counts of galaxies stop swinging wildly with direction and position, and the universe looks statistically uniform and isotropic. That's the cosmological principle in action. It's the reason you can talk about one expansion history and one distance redshift relation for the whole map. Below that smoothing scale, the Webb is obvious. Above it, the noise cancels and the universe behaves like a smooth fluid. What does Webb add that you didn't already get from huge ground surveys? Reach and precision at high redshift. NIRCam is sensitive enough to trace over densities of very young galaxies where the first filaments are turning on. NIRSpec then stacks up redshifts across those overdensities, converting a 2D ski pattern into a 3D slice of the Webb. You don't just see clumps, you watch elongated chains of galaxies at the same redshift, flowing along the same spine, and you measure their internal gas with line diagnostics. In some fields, integral field spectroscopy even shows velocity gradients that hint at inflow along the filament, not random motion. This matters because the Webb doesn't appear all at once, it grows. The earliest filaments are thinner, the contrasts are lower, and the gas is more pristine. As time passes, halos merge along those paths, shocks heat the medium, metals spread, and the intersections light up as protoclusters. Webb catches that ramp up at Z greater than 6, where optical surveys fall off, so you can link the first strands to the mature highways you see at lower redshift. When you later look at a massive cluster in the modern universe, you are looking at a node that was already being fed by skinny high-speed lanes in Webb's era. There's a practical link to reionization too. Ionized bubbles carve through the neutral intergalactic gas more easily along the dense paths where galaxies are packed. If you see Lyman-α in one region and not in another at the same redshift, chances are you're comparing a filament already full of star-forming galaxies to a quieter void still mostly neutral. That makes Lyman-α a tracer of the Webb's first light as much as a tracer of transparency. Webb supplies the needed spectra to tell which is which. Population work is where this gets strong. With hundreds of secure redshifts per field, you can measure how galaxy numbers rise from void to sheet to filament to node. You can see how sizes and star formation rates change within environment, and you can test whether metal enrichment runs ahead along the densest routes. The trend is clear already. Denser environments light up earlier and harder because gravity funnels fresh gas inward along the Webb and inflow fuels stars. Add lensing fields like SMACS 0723, and magnification lets you probe even fainter members of the same structures, tightening the statistics. All of this still respects the smoothing scale. Zoomed out to hundreds of megaparsecs, you average over many filaments and voids and the signal flattens, which is exactly what the principle of homogeneity demands. That agreement between local complexity and global simplicity is not an aesthetic choice, it's a quantitative check that your map, your geometry, and your physics hang together. So where does this leave you? With a live picture of assembly, the Webb provides the roads, matter moves along them, galaxies grow where the traffic meets, and Webb shows you those roads switching on at very high redshift. Once you see that, the next step is obvious. If the highways feed the cities, when did the traffic peak? And when did most of the stars in the universe actually form? When did the universe do most of its star building, and why wasn't the maximum at the very beginning? The peak hit around redshift 2, about 3.5 billion years after the Big Bang. Astronomers call it cosmic noon. Before that, the star formation rate density climbed fast as fresh gas flowed along filaments into young galaxies. After that it faded, steadily, as fuel was heated, blown out, or locked into long-lived stars. That rise and fall is not a guess. It's a measured curve built from many surveys, and it sets the look of the galaxies you see around you today. Here's what the peak means in plain terms. At Z, approximately 2, the average universe was busier per unit volume than it is now by an order of magnitude or more, with mergers common, disks gas-rich, and starbursts frequent. Massive galaxies ran hot, then many of them shut down, quenched, and drifted into quieter lives. Smaller galaxies kept forming stars longer, but even they slowed. By today, the cosmic factory is still open, just on the night shift. That history explains why big ellipticals are old and red, why spirals like the Milky Way carry mixed-age populations, and why dwarf galaxies scatter in behaviour depending on how long their gas supply lasted. Where does Webb change this story? It fills in the early rising side of the curve with real physics instead of extrapolation. The key is access to the rest frame optical lines that track star formation directly. H-alpha, a bright hydrogen line, scales with the number of massive short-lived stars being born. O3, at 5007 angstroms, paired with H-beta, tells you about ionization and, with ratios, metallicity and dust. At high redshift, those lines are shifted into the infrared, exactly where Webb's NIRSpec and MIRI work. That means you don't have to infer star formation rates from ultraviolet colour alone, which is sensitive to dust and age. You can read them off from emission lines with known calibrations, then correct for dust using the Balmer decrement, the H-alpha to H-beta ratio. Practically it goes like this. NIRCam finds the candidates and gives you sizes and surface brightness. NIRSpec takes spectra for hundreds at once, pulls out H-alpha when it's in band, grabs O3 and H-beta at even higher redshift, and resolves line widths well enough to estimate dynamics. Where H-alpha slides beyond NIRSpec, MIRI picks it up. You turn those measurements into star formation rates with uncertainties, not hand-waving, and you place each galaxy on a well-calibrated axis of redshift, luminosity, size and environment. Stack many fields, correct for volumes and selection, and you trace the true rise toward cosmic noon rather than sketching it. Webb's early catalogues show exactly what you'd expect if the peak is real and early growth was brisk. The number of vigorously star-forming systems ramps up from Z approximately 10 towards Z approximately 2, and their typical sizes grow as gas settles and disassemble. The specific star formation rate, the rate per unit stellar mass, is high early on, then declines, matching a picture where fresh gas is cheap at first and harder to come by later. Emission line ratios indicate that metals appear quickly, so second-generation stars enrich their surroundings fast, which feeds back into cooling and keeps the early engine running efficiently. This isn't a scrapbook of pretty objects, it's a time-lapse. At Z greater than 8 you see compact, intense builders, sometimes lensed, punching above their weight. By Z2, the factory floor is in full swing, with thick, turbulent disks lit by H-alpha and O3s. Across kiloparsecs. Past the peak, the same diagnostics show declining rates, growing bulges, rising quiescent fractions. Because the lines are physical meters, you can compare apples to apples across all these epochs, not just colours that shift with dust. Environment threads through this. Along filaments, where inflow is steady, line strength spikes, sizes inflate, and metallicities climb. In lower density regions, the ramp is slower. Webb spectroscopy pins the redshifts that let you sort galaxies into those environments cleanly. So you're not mixing cosmic noon in a protocluster with cosmic noon in a void and calling it average. That separation tightens the star formation history and keeps modelers honest about how gas supply and feedback work in different settings. Uncertainties are there, and they're manageable. Dust corrections carry error bars, so you measure both Balmer lines when possible, and you cross-check with infrared continuum where detected. Selection effects can bias counts toward brighter, higher equivalent width systems, so you fold the selection function into the volume corrections, and you use lensing fields to probe fainter members. Line blending can hide weaker features at low resolution, so you step up to higher resolving power when you need unambiguous profiles. Each fix is built into the observing plan, not patched after the fact. Add it up and the picture is tight. The universe ramped up from the first billion years toward a sustained planet-making frenzy around 3.5 billion years, then eased off. Webb supplies the hard line-based rates that make the early half of that curve real, not extrapolated, and links what you see in teenage galaxies to the old metal-rich systems around you now. That is why your 93 billion light-year bubble doesn't feel like disconnected snapshots anymore. It reads like a continuous build with timestamps and mile markers. If star formation was already this discipline this early, another question jumps out. How did the raw chemistry get there so fast, and can we actually see heavy elements lighting up beyond redshift 10? Right on the heels of the first stars. How fast did real chemistry switch on, and do we actually see heavy elements blazing beyond redshift 10? Not as hints, but as hard detections. Webb plus ALMA just answered, very fast and yes. In Jade's JWST 14-0, a galaxy locked at Z equals 14.18, ALMA picked up a brighter 3 88 micron line, which means ionized oxygen was already in place only approximately 300 million years after the Big Bang. Oxygen doesn't exist without earlier stars forging it and spreading it, so this is direct proof of rapid metal enrichment on an aggressive clock, not a hand wave. The ALMA line also sharpened the redshift with exquisite precision, anchoring everything else you derive about size, luminosity, and star formation rate. Now, look at GNZ 11. Z equals 10.6, already famous and now even more interesting. Webb spectra show unusual nitrogen features and elevated nitrogen to oxygen ratios. Nitrogen at these levels so early points to intense, very young stellar populations, fast recycling through massive stars, or more exotic channels that dump nitrogen into the gas quickly. Either way, the chemistry is not crawling, it's sprinting, and the timescale leaves little room for slow, gentle enrichment. You also need the rest optical workhorses to turn it looks bright into here's the rate. That's where NIRE steps in. By pushing to longer wavelengths, NIRE delivers H-alpha and O3 for Z greater than or equal to 10 sources, up to around approximately 12.3 in current reports, so you can read off star formation rates from recombination light, check dust with the Balmer lines when both are in hand, and pull metallicities from robust line ratios. These are not colour tricks, they're direct physical diagnostics, and they turn a red smudge into numbers you can compare across cosmic time. Put the pieces together and the early timeline tightens, a spectroscopically pinned galaxy at Z, approximately 14 with the brighter 3, says second-generation stars were already active by approximately 300 million years, injecting oxygen into H2 regions. GNZ 11's nitrogen features add pressure on models to explain rapid M production without long delays. NIRE's rest optical lines let you measure star formation and metal content at Z greater than 10 with the same tools used at lower redshift, so you aren't stitching epochs with inconsistent yardsticks. The consequence is simple and sharp. The far edge of your observable map isn't just dotted with proto-galaxies, it's lit by real, measured chemistry, locked by spectra, and timed by lines that leave no wiggle room. If lines are doing this much heavy lifting, you should ask the obvious question next. When does a claim count? And what separates a pretty colour from a distance you can defend line by line, break by break? How do you know that red dot is truly a galaxy 13 billion years back, and not a closer imposter wearing dusty makeup? You get a spectrum, and you let physics decide. Photometric redshifts, those colour-based guesses, are useful for triage, fast and broad, but they can be fooled by dust, extreme emission lines, or odd stellar populations. Spectroscopy is the audit. You look for hard anchors, the Lyman break where flux crashes blueward of a specific wavelength, the Lyman-α line when it survives the intergalactic medium, and the rest optical workhorses, O3, H-beta, H-alpha, shifted into the infrared. Match the features with the right spacing and the redshift locks. No hand-waving, just wavelengths and ratios. NIRSpec is built for this job. It spans roughly 0.6 to 5.3 microns and lets you choose resolving power from quick and faint R1000 up to about R approximately 2700, when you need to separate blended lines, measure velocities, and read line profiles cleanly. At low resolution, you catch continuum breaks and strong lines in single shots. At higher resolution, you pull apart O3 from H-beta. You see asymmetric Lyman-α shaped by outflows, and you turn line widths into crude dynamical masses. Resolution isn't style, it's the difference between maybe high Z and definitely Z at equals 10.6, with a 1 sigma error bar. The multiplier is the microshutter array. About 248,000 addressable shutters, each a tiny door you can open or close. You program a mask to match the targets from your deep NIRCam image, open hundreds of shutters on galaxies you actually want, and close the rest to block sky and neighbours. One pointing, hundreds of spectra, minimal contamination. Repeat with new masks and a single field becomes a redshift factory. This is how you turn a pretty picture into a 3D catalogue fast enough to matter. Once the redshift is secure, the rest flows. The continuum shape tells you about age and dust. H-alpha, when in band, gives you an immediate star formation rate. H-beta plus O3 fills in at higher redshift, and with the Balmer decrement corrects for dust. Line ratios give metallicity and ionization state. Equivalent widths track burstiness. With R approximately 2,700, you even get velocity offsets between lines, a handle on outflows and inflows. Every parameter ties back to a measured wavelength, not a colour guess. This is why spectra beat anecdotes. Photometric candidates can stack up at extreme redshift because dusty medium redshift galaxies masquerade as dropouts, and extremo 3H beta emitters at Z, approximately 2 to 3, can fake very red colours. A spectrum breaks the tie in minutes. You see the wrong set of lines, it drops out of the high Z bin. You see the Lyman break plus the right rest optical lines. It stays, with a firm distance and a clock time. Your luminosity functions, mass functions, and reionization timelines stop drifting with selection bias, because the interlopers are gone. Scale is the payoff. Multiplexing through the microshutters gives you enough confirmed objects to measure distributions, not just trophy cases. You can map how many galaxies live in each redshift slice, how their sizes and star formation rates spread, how metallicity evolves, and how environment shifts those numbers along filaments and into nodes. Stack fields, blank, lensed, proto-cluster, and you beat down cosmic variance. Tie the spectroscopy to precise imaging, and you get size-mass SFR relations with real depth, not blurred by photometric scatter. All of this drops into the same coordinate system you've been building. Redshift becomes comoving distance through lambda CDM, so each confirmed object lands at a clean spot inside your 93 billion light-year bubble. You're not filling space with maybes, you're planting flagged points with uncertainties you can propagate. That is how a map earns the word map. And because the process is repeatable, same filters to select, same shutters to target, same resolutions to confirm, you can compare one program to another without shifting baselines or reinventing calibrations every time. There are limitations, and you handle them. Lyman-α can be suppressed by the neutral gas, so a non-detection isn't an automatic veto. You lean on the continuum break and other lines. Sky background rises toward the long wavelength tin end, so exposure times go up. You plan masks to balance depth and yield. Source confusion happens in crowded fields. You use the sharp imaging to place shutters precisely and avoid overlaps. None of that undermines the core. Spectra convert candidates into coordinates. Net result, deep fields stop being galleries and start being surveys with clocks. The microshutter array turns observing time into hundreds of clean redshifts per pointing. NIRSpec's resolution separates the physics. The line set, Lyman break, Ly-alpha, O3, H-beta, H-alpha, locks distances, ages, and rates. That efficiency is how you fill a vast 93 Glysphere with precise 3D points, not photometric maybes, and it's why the early universe now reads like a timeline instead of a rumour. You've nailed distances with lines, but to keep the whole scale honest, you still need the nearby yardstick that everything ultimately hangs on. Which local rulers still set the baseline, and has Webb changed their verdict enough to matter? If the BAO and the CMB already lock the big geometry, why do you still need a backyard ruler? And why does everyone care about a handful of blinking stars and dusty galaxies? Because every cosmic distance, every size, every luminosity, every age, ultimately needs a local anchor you can audit end to end with plain physics and repeatable measurements. That anchor is the distance ladder. First rung parallax the simple geometric shift of nearby stars against the background as Earth moves around the Sun. Space missions like Gaia nailed that baseline with micro-arc-second precision, so you can trust the distances to thousands of calibrator stars. Second rung Cepheids, pulsating variables whose period is tied to their true brightness. Henrietta Leavitt gave you the relation. Modern calibrations refine it with metallicity and colour terms, and parallax fixes the 0 point. Third rung, Type Ia supernovae, those near standard explosions in distant galaxies whose peak brightness can be normalised with light curve shape and colour. Tie the Cepheid distances in the supernova host galaxies to the supernova brightness, and you can read distances out to hundreds of megaparsecs. That three-step chain is how the SH0ES team lands on an expansion rate around 73 km per second per megaparsec, with percent-level uncertainties, and that in turn is why the late universe side of the Hubble tension won't go away. Now, where does Webb enter the picture, and what exactly is it testing? The ladder's soft spots have been known. Crowding and blending in HST images of Cepheids, dust extinction that's hard to model in the optical, and photometric cross-calibration between instruments and filters. Webb's infrared eyes go straight at those. Longer wavelengths cut extinction dramatically, so Cepheids dim less and their colours are more honest. The point spread function is sharper in the infrared from space than what you typically get from the ground, and the background is low and stable so you can separate a Cepheid from its neighbours in a messy, star-forming spiral. When you resolve the field better, the amplitude and mean brightness of each pulsation stop being biased by unresolved faint companions. If the ladder were being propped up by crowding, this is where it would snap. Teams have done the side-by-side checks you'd expect. Find the classic supernova host galaxies that anchor the ladder, the same ones imaged with HST, point NIRCam at their Cepheid fields, then measure the periods and mean magnitudes again in the infrared. Cross-calibrate the filters, track 0 points, compare object by object, and ask a hard question: how much do blending and dust shift the distance scale? The answer so far is not enough to make the local H0 fall to 67. The scatter tightens, the systematic shrink, but the central value stays high within errors. That means Webb is not quietly dissolving the tension by revealing a photographic illusion. It's stress testing the rung and finding it sturdier than critics hoped. Cepheids aren't the only rung, and Webb is doing the same cleanup elsewhere. Tip of the red giant branch distances depend on catching the sharp cutoff in the red giant luminosity function. In metal-rich crowded galaxies, the cutoff can blur. Infrared imaging resolves the brightest giants better and reduces metallicity and dust sensitivities, sharpening the tip and giving a cleaner distance. Mirrors, long-period variables in the asymptotic giant branch, offer another route, less sensitive to crowding and with well-behaved period luminosity relations in the infrared. Webb observations raise their weight in the ladder by boosting sample sizes in key hosts. Geometric megamasers, the gold standard water masers orbiting supermassive black holes in nearly edge-on disks, benefit when Webb images and spectroscopy cleanly separate host properties and help tie the mesa distances to the same photometric systems used for Cepheids and TRGB. Each method has different systematics, and the more you can cross-calibrate them in the same galaxies, the less room there is for a hidden bias big enough to shift H0 by 5 to 6%. You also want cross-checks that don't touch the ladder at all, and this is where the broader network matters. BAO with supernovae gives you a model-like path to H0 that tends to prefer lower values. Strong lens time delays, where you measure how long it takes multiple images of a variable source to flicker relative to each other, Deliver H0 once you model the lens mass distribution accurately. Those results often land in the middle to high range. Fast radio bursts bring dispersion measures tied to the electron content along the line of sight. With enough localized FRBS and secure redshifts, that method can become a new, independent distance probe across a wide redshift span. Gravitational wave standard sirens, binary neutron star mergers that shout their absolute distance from the amplitude of space-time ripples, are ramping up. Add a clean electromagnetic redshift for the host and you have a one-step H0. Webb doesn't set these methods' physics, but it sharpens the inputs. It resolves hosts in crowded fields, it nails redshifts in the infrared when optical lines are weak, and it images lens galaxies and their environments with the fidelity you need to control mass model systematics. None of this is academic quibbling, because every early universe claim you make inherits the scale you choose. Change H0 and the luminosity distances shift, so intrinsic brightnesses shift. Change those and star formation rates derived from luminosity shift. Number densities change when you convert flux limits to mass limits. Ages at a fixed redshift move by hundreds of millions of years at the earliest epochs. Webb's new high redshift conformations sit on this base, so you want the base trustworthy. The early universe inference from the CMB and BAO says 67 point something. The local ladder, scrubbed with Webb's infrared imaging for crowding and dust, still says roughly 73. Both have been audited. Neither has coughed up a fatal error so far. So what do you do practically while the community sorts the last few percent? You carry both scales in your head, you propagate uncertainties honestly, and you watch for convergence as the independent methods mature. Webb has already chipped down the plausible ladder systematics, blending, dust, photometric calibration, and the tension still stands. That keeps the stakes high, because if both sides remain clean, you're forced to consider whether late-time physics, early-time physics, or subtle, correlated systematics are at play. New neutrino physics, evolving dark energy, spatial curvature at a level not captured by current models, or complex astrophysical biases tied to environment, these are the kinds of possibilities that sit on the table when two careful rulers disagree. Meanwhile, the headline size of your observable universe, about 93 billion light-years across today, doesn't swing wildly with this fight. That diameter comes from the particle horizon in a geometry pinned by him to the CMB and BAO. Nudge H0 within today's error bars and the radius shifts only mildly. Your map stays the same shape and the tick marks get a tiny re-etch. Webb's role is to make sure the nearby ticks are carved with the same precision as the far ones. So when you overlay early galaxy physics on top of the global geometry, the two layers line up. One last point that often gets missed. The distance ladder is not a monolith, it's a suite of interlocking methods, each with its own failure modes. Webb doesn't have to fix the entire ladder to be decisive, it just has to reduce enough key systematics that, if a big bias existed, it would have shown up by now. With sharper Cepheid fields, cleaner TRGB tips, better mirror samples, and tighter host imaging for supernovae, the door for an easy, single-parameter rescue has narrowed. That's why the conversation is shifting from maybe the ladder is wrong to either there's a shared subtle bias across several methods, or there's new physics in the expansion history. Either path is interesting. Either path matters for how you place every point inside your 93 billion light-year bubble. So your working summary is simple. Parallax to Cepheids to supernovae still sets the local yardstick, and the SH0ES value around 73, with percent-level precision, continues to drive the late-time side of the H0 tension. Webb's infrared imaging hit the suspected weak spots, crowding, blending, dust, and did not find a smoking gun big enough to erase the discrepancy. Independent yardsticks, BAO, time delays, FRBS, standard sirens, are tightening the cross-checks that bind the whole map. The radius of the observable universe stays solid, but the exact route you take to get there is still under active, serious test, and Webb is keeping the pressure on. If you've secured your rulers and you trust your anchors, the next limit to face isn't a calibration problem at all, it's a horizon problem, a hard boundary set by space-time itself. How much of the universe can you ever see, even in principle, and how does that cap the questions you can answer, no matter how powerful your telescope becomes? Why are there parts of the universe you will never see, no matter how early you start looking, no matter how good your telescope gets? Start with two hard boundaries that sound similar, but do different jobs. The particle horizon is the distance to the farthest place whose light has had time to reach you by now. That sets today's observable radius at about 46.5 billion light-years. In comoving terms, the language where we factor out expansion so coordinates don't drift. Double it and you get the familiar 93 billion light-year diameter. Different boundary, different meaning, the event horizon is the maximum distance from which light emitted right now could ever reach you in the future. Because expansion is accelerating, that limit is only about 16 billion light-years in proper distance today. Anything sending a signal from beyond that shell starting now will never get to you. Not in any amount of waiting. Keep the rolls straight, because confusion here breaks your intuition. The particle horizon is about the past. It marks how far the oldest arriving photons have travelled since the universe became transparent. The event horizon is about the future. It marks a limit set by how fast space will keep stretching. One tells you what you can see today, the other tells you what you can ever see from signals launched now. They are not equal, and they do not move the same way with time. The particle horizon grows as more ancient light finally arrives. The event horizon is a consequence of dark energy driving accelerated expansion, and that acceleration prevents some future light from ever closing the gap. This is easier to picture if you think in terms of light cones and a moving ruler. Your past light cone collects everything that has already reached you, climbing back in time to the microwave background at about 380,000 years after the Big Bang. Your future light cone is everything your own signals can reach if you send them now. The event horizon sits outside that future cone's overlap with the rest of the universe, a no-contact zone created by expansion outrunning the ability of light to catch up. None of this is about a speed limit being broken. Nothing moves faster than light through space. Space itself is stretching, and that changes what reachable means. So why is the event horizon as small as roughly 16 billion light-years when the observable radius is almost 3 times larger? Because most of the faraway light you see today did not start now. It started long ago, when the universe was more compact and expansion had not yet accelerated as much. Those photons have been surfing the expansion the whole way, losing energy, stretching in wavelength, but still making headway until they hit your telescope. If a distant galaxy beyond 16 billion light-years sends a flash today, the expansion between you and it will grow faster than the flash can eat into the gap, and the signal never arrives. If that same galaxy sent a flash billions of years ago, you can still receive it today or tomorrow, depending on when it left and how the expansion history integrates. That's the split between already on the way and too late to ever start. Now push the clock forward and ask a scarier question. Will you see more of the universe if you wait a very long time? Yes, but only up to a ceiling. The particle horizon keeps creeping outward as additional ancient photons, emitted long ago within your causal reach, finally arrive. In our best fit cosmology, that future visibility limit asymptotes around 62 billion light-years in comoving radius. That is bigger than today's 46.5, but far smaller than infinity. You will eventually watch new, extremely redshifted sources from slightly farther comoving distances light up your map. Then the growth stalls. Beyond that, even the oldest photons that could have been headed your way will never make it to you, because the accelerating expansion stretches their paths too much. Do not mix these horizons with the Hubble radius, the distance where recession speed equals the speed of light today. The Hubble radius is a local time-dependent scale set by the current expansion rate, useful for intuition but not a true horizon. Light can and does reach you from beyond the Hubble radius if it started at the right time, and the expansion history cooperates. The particle horizon and the event horizon are global statements about what signals have arrived and what signals can ever arrive, integrated over the entire history and future of expansion. That's why they matter for what's knowable, not just what's convenient to measure. There are direct observational consequences you should keep in mind as a working mapmaker. First, galaxies you see near today's edge will fade and redshift with time. Their light stretches into longer and longer wavelengths. Their surface brightness drops, and eventually many will slide out of the wavelength band your instruments can detect. Second, more distant, already en route photons will trickle in from slightly farther comoving shells, so the sensors fills out a bit more even if you build no new telescope. Third, no instrument can pull in a signal that the event horizon forbids. That's not a technology problem, it's a geometry problem. Perfect mirrors, zero noise, infinite patience, none of that lets light emitted today from beyond the event horizon cross the ever-growing chasm. Dark energy is the culprit that makes the event horizon real. When the universe's expansion accelerates, the scale factor grows fast enough that distant regions recede from each other more and more quickly. Again, nothing is outrunning light locally. The metric itself is changing. In such a space-time, there is a finite sphere beyond which light sent now is forever stranded. If acceleration continues as a cosmological constant, that stranded region persists, and the long-term universe becomes a set of island patches where only gravitationally bound structures remain in causal contact. That is the stark, late-time picture. A sky where local clusters stay visible, but most distant galaxies slip into darkness, their light redshifted into wavelengths so long that detectors cannot meaningfully recover them. Where does Webb fit into this story that sounds, frankly, bleak? Webb's job in your lifetime is not to beat horizons, no mission can do that, but to push the seen edge of structure as close as physics allows to the microwave wall without ever touching it. Webb is optimized for exactly the photons that expansion has stretched from the ultraviolet and visible into the infrared. That means the first galaxies, the early star clusters, the compact high-surface brightness systems that switched on a couple of 100 million years after the Big Bang. Spectroscopy nails their redshifts. The lines give you star formation rates and metallicities, and lensing fields multiply your reach. Each confirmed source near the frontier is a new pin in the inner surface of your observable bubble. This push matters doubly because the last step before the microwave background is a foggy era, reionization, where neutral hydrogen blocked a lot of ultraviolet light. Webb skirts that barrier by catching lines and breaks that leak through ionized bubbles, and by following rest optical lines at yet longer wavelengths. It will not detect the CMB itself. That's a microwave job for other telescopes. But it can map the ramp up to transparency with enough detail that the timeline from ripples in the CMB to bright galaxies feels continuous, not stitched. That is as close to the wall as you're ever going to see in starlight. Expect the frontier to shift, but modestly. As deeper programs stack exposure time and more strong lensing fields are analysed, the highest confirmed redshifts will nudge higher. The statistics at Z greater than 10 will thicken, and the early chemical diagnostics will sharpen. That will push your mental map's inner shell closer to the CMB by tens of millions of years here and there, not by a billion. The reason is simple. The window between recombination and the first sustainable light sources is short, hundreds of millions of years, and we are now probing much of it. The real gains will come from turning a few spectacular detections into a population-level census with clean selection functions and hard spectra. There's another, subtler frontier Webb helps with. While horizons box you in, the redshift drift and aging of the sky. Over very long times, the expansion rate changes slowly, and the spectra of distant galaxies would shift by tiny amounts detectable only with absurd patience and stability. You won't measure that drift with Webb, but by securing today's Heiser spectra and line identifications, you lay down the reference frame that future facilities will use to attempt it. Even here, horizons set the ultimate limits, because the sources themselves will dim and slide to wavelengths where detection is impractical, but the baseline you establish now is the only practical way to try. So your practical summary is stark and empowering at once. The particle horizon is your how far has light gotten boundary today, around 46.5 billion light years. The event horizon is your what can ever reach you if it starts now boundary, around 16 billion light years. Wait long enough and the observable radius grows toward roughly 62 billion light years as the last eligible ancient photons arrive, but it stops there. No telescope beats those rules. Webb can't either. What Webb can do, and is already doing, is pack the interior with verified sources right up to the physical limits. Deep imaging to find candidates, multiplex spectroscopy to lock distances, lensing to boost the faint, and line diagnostics to turn colour into physics. That is how you convert a hard geometric ceiling into a full three-dimensional atlas that feels complete inside the part of the cosmos you can actually audit. Now step back and connect all the threads. You stand at the centre of a time-defined bubble. You know why its edge sits where it does. You know why some regions will never talk to you. And you've watched Webb push the frontier until it almost brushes the microwave wall. The only question left is the human one that still matters for scale. After all the numbers, after all the spectra, what does this size do to your sense of place? And how do you carry that 93 billion light-year bubble in your head without letting it turn into just another big number? How big is 93 billion light-years when it actually lands in your head? Not on a slide, not as a trivia fact, but as a map you can trust. Start with the part Webb changed first. The empty-looking stretch between the baby universe in microwaves and the first galaxies you could actually confirm. Before Webb, that gap felt wide. You had the CMB at 380,000 years, then a long, dim climb to the first secure galaxies at redshifts around 8 to 10, with plenty of debate about which candidates were real. Webb hit that gap with infrared sensitivity and fast spectroscopy, and the frontier moved. You now have galaxies at Z approximately 10 to 14, pinned by spectra, not colours, sitting roughly 250 to 500 million years after the Big Bang. That compresses the no man's land between first light and the CMB. The bubble you live in doesn't grow in diameter because of that, but it feels fuller, older, bigger, because the early time slices now hold real sources with measured positions, ages, and chemistry. You see that shift in every metric you care about. The Lyman break shows up where it should. For Z greater than 10, Lyman-α appears in patchy windows at very high redshift when ionized bubbles open paths, O3 and H-beta lift out of the noise and fix distances where optical telescopes couldn't, and, when available, H-alpha locks star formation rates with the same physics you use at lower redshift. The result is not a handful of trophy objects, but growing samples with consistent selection, consistent spectroscopy, and consistent model fits. You can calculate real distributions, luminosity functions, mass functions, equivalent width distributions, and those distributions look like the early ramp toward the later peak at Z at approximately 2, not a random scatter. That's what fuller means here. Not feelings, but counts. Older comes from the chemistry. Catching bright O3 at Z, greater than 10, and nitrogen features in standout systems like GNZ11 tells you metals were already present, and present in useful amounts. Only a few 100 million years in, that means at least one round of starbirth and supernova happened before the light you're seeing. The interstellar gas wasn't pristine. Cooling was faster than the most conservative models assumed. The early universe didn't wait around for a slow ignition. It lit, it enriched, it built on a tight clock. When you add this to the new redshifts, the early part of the timeline stops looking like a fog and starts looking like a sequence you can annotate. Bigger is about geometry you can defend. The number 93 billion light years is not a loud claim. It's the comoving diameter set by a model that matches the CMB, the BAO standard ruler and large-scale structure. The CMB supplies the sound horizon and the initial conditions. BAO reads that ruler out across billions of light years at later times. Together they pin curvature near flat and deliver a distance redshift relation that is stable. The distance ladder, calibrated locally by parallax, Cepheids and Type Ia supernovae, cross-checks the same relation from the nearby universe out. Webb's infrared imaging has shoved on the ladder's weak points, crowding and dust in Cepheid hosts, and so far the ladder holds its high H0 without collapsing to the CMB value. That tension is real, but it does not rip the 93 Gle diameter apart. The particle horizon radius depends on the whole expansion history and on early universe anchors. Tweak H0 within today's bounds and the radius barely nudges. That's why you can say the number with a straight face while admitting there's still work on the last few percent. You might ask whether the web of matter inside that bubble is truly mapped well enough to deserve words like Atlas, and the answer is trending yes. On small scales, you see the filaments and nodes where galaxies form, and you know from the larger surveys that on scales above about 100 megaparsecs, statistics smooth out and the universe is uniform enough for a single geometry to make sense. Webb's job in that context is not to cover the whole sky, it's to provide high redshift fidelity in key regions. Deep fields, lensing fields, proto-cluster fields. Each contributes dense, secure redshifts and real physics. NIRCam finds the right targets. NIRSpec's microshutter array converts them into hundreds of spectra per pointing, and integral field modes turn bright objects into 3D data cubes with gas motions and line ratios. Snap those cubes onto bio-calibrated distances, and the map lines up from the first few 100 million years all the way to the present day. You also have hard boundaries that keep expectations in check. The particle horizon sets today's observable radius at approximately 46.5 billion light-years. The event horizon sets the reach of light emitted now at approximately 16 billion light-years, and the future visibility limit asymptotes near approximately 62 billion light-years as the last eligible ancient photons arrive. No telescope, not even a perfect one, can beat those limits. That's important because it tells you what the full in fuller can and cannot mean. You can fill the interior with confirmed sources, you can sharpen the early edge by reducing guesswork, you can never see past the time barrier, defined by transparency and the late time acceleration. Webb is built to operate right up against the allowed edge, and that is exactly what you're watching happen. The crosslock is the safety net. BAO and the CMB anchor geometry, the ladder anchor's local distance, lensing checks, convex mass maps, time delays, and standard sirens enter as independent auditors, and Webb threads through the high redshift gaps with clean lines and secure redshifts. When all those methods point to the same distances within errors, you trust the conclusions you draw about galaxy sizes, luminosities, and star formation rates. When one of them deviates, you know exactly where to dig. That is a more valuable kind of certainty than a single best number, because it's robust to surprise. It's the difference between a claim that falls if one instrument is wrong and a claim that stands because 5 unrelated tools agree. Keep the numbers straight while you're absorbing the scale. Age today, about 13.8 billion years. Observable radius today, about 46.5 billion light-years in comoving distance. Event horizon today, about 16 billion light-years in proper distance for signals launched now. Future visibility limit, about 62 billion light-years in comoving radius. Peak of cosmic star formation, around Z approximately 2, roughly 3.5 billion years after the Big Bang. Confirmed galaxies at Z approximately 10 to 14, light emitted about 250 to 500 million years after the Big Bang. None of these numbers stands alone, all of them are tied together by spectra, by rulers, by tested models. That is why the map feels solid instead of fragile. This is also why the early universe headlines you've seen lately really matter. A single object at Z approximately 14 with bright oxygen is not a stunt. It is a boundary condition on how fast enrichment must have happened. A Lyman-α detection at Z approximately 13 in one field, paired with a non-detection at the same redshift in another, is not noise, it is a map of reionization patchiness. A lensing deep field that produces dozens of secure Z greater than 10 spectra in one pointing is not a pretty poster. It is a throughput proof that converts scarce telescope hours into a real 3D census. Each piece is a data-backed move that takes "we think" and turns it into "we can show." You could stop there and call it enough, but you can also press the operational point. This progress came from a specific set of capabilities working together: deep, cold infrared imaging to find the faint, high-efficiency multiplex spectroscopy to confirm at scale, gravitational lensing to boost the faint and resolve the small, standard rulers to lock distances across time, local anchors to set 0 points you can audit. No single part is sufficient, every part reduces a different failure mode. When they all point the same way, you have reach, you have precision, and you have a path to push farther without losing trust in the answers. So how do you carry 93 billion light-years so it doesn't turn into background noise? Treat it like a living boundary with a ledger full of entries. Webb is filling the ledger on the inside face at the youngest times where the map was thin. BAO and the CMB keep the ledger's columns aligned. The ladder keeps the first rows honest. Horizons tell you where the ledger stops, not because you got tired, but because the universe draws a line. If you hold those ideas at once, the number stops being abstract. It becomes a scale you can use. Here's the straight closing line you can repeat without flinching, because it's tied to real data, real spectra, and cross-checked geometry. You live at the center of a 93 billion light-year bubble of knowable cosmos, and Webb just pushed its inner edge closer to the beginning than anyone thought possible. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.